Okay, now we are going to solve problem number 6. So the problem says here the chain link in the figure below is made of oil quenched alloy steel with yield strength and tension as 1250 megapascal and an endurance limit in reverse bending of 600 megapascal. You see here this is a chain link with some given proportions. You see here the radius of this circle is R, capital R. The diameter of this pen here is small d. This distance here between these two lines is small a, and the thickness of this part perpendicular, if you look from the top here, so it is W, right? The material is characterized, so the yield strength of the material is given and the endurance limit in bending is given as well. So the link here is subjected to tensile load, which rises to a maximum on the tight side of a low speed drive and decreases to 0 on the slack side as the link passes over the driving sprocket. So normally the chain, it's like your bike's chain. There is one tight side and one slack side, and if it is not, there is no pretension. So normally the slack side force is 0. So which is the case here. So this same link at some point it's going to be subjected to a maximum force, and at other point when it rotates to on the opposite side, the force is going to be 0. So it will keep like going between maximum force, minimum force, maximum force, minimum force, and this is obviously fatigue. So the actual stress concentration factor is given, which is 3.46. It is K sub F here is given straight away, based on the minimum cross-sectional area. So if you look at this chain link here, you'll find that the minimum cross-sectional area is across the whole here. So this is the cross-sectional area that we are going to consider. When the link proportions are, this R value is the same as the diameter of the pen. So R is equal to D, is equal to 4 times the thickness of the link. And this value A is greater than the diameter of the pen. Find the dimensions of a link capable of transmitting 50 kilogram force. This is the maximum force, obviously. The minimum force is 0, with a factor of safety 1.25 based on the yield strength. So in this case, we're going to focus on the cross-sectional area, and once we find the cross-sectional area and using these proportions, we'll be able to find all the values. Again, yield strength of the material is given, is like 1250 megapascal. There is a mistake here. This is supposed to be Newton per millimeter squared. The endurance strength of the material is given 600 Newton per millimeter squared. The maximum force is given in kilogram force. So you need to multiply this force by the gravitational force to convert it to Newton. So it's times 9.81. So this gives us 4,905 Newton. The minimum force is 0, and the fatigue stress concentration factor, or the actual value of the stress concentration, is given as 3.46 based on the minimum cross-sectional area, which you see. Then the proportions are given as the radius of the link here, or capital R, is equal to the diameter of the hole is equal to 4 times the thickness of the link. And the factor of safety again is given. So let's consider that the unknown here is our cross-sectional area, and then based on the Soderberg equation, we can find these values. So if we consider the minimum cross-sectional area across the hole, it is 2R minus D times W. So going back here, because the distance between here to here is R, so the full width is 2R. If we take away from this 2R the diameter, so it's 2R minus D, and then multiply by the thickness, which is W. So this is exactly what we have here, 2R minus D times W. But remember the proportions. It says the D is equal to R, so we can replace this D by R. So it's going to be 2R minus r, so this bracket boils down to r, and then there is a relation between w and r again. If I go back here, see, so the r here is equal to 4w, so w is equal to r over 4. So if we replace this w by r over 4, so it's r over 4 here multiplied by r, which is r squared over 4. And again, going back to the proportions, we know that r and d are equal, so this could be also d squared over 4. Okay, so the cross-sectional area is simply d squared over 4. The minimum force is 0, and the maximum force is given, was calculated based on this equation here, 500 times 9.81. So based on that, the mean force is equal to F max over 2, and the reversed force is also F max over 2. If you use the mean and the reversed force, or mean and reversed magnitude definitions. Maximum plus minimum over 2 for the mean, maximum minus minimum over 2 for the reverse. So both are equal here because the minimum force is 0. So the mean and the reversed forces are the same, which is the maximum force divided by 2. So in this case, if we use the Soderberg equation for the tensile or the direct stress case, so we multiply the top and the bottom of this equation by the cross-sectional area. So this means that we have an area here, and then when you multiply the mean stress by the area, it gives you the mean force. Multiply by the reversed stress by the cross-sectional area, it gives you the reversed force. So we can rearrange this equation because we know the factor of safety. So in this case, we can rearrange this equation to find the value of A. Once we find the value of A, we can equate it to this d squared over 4, and then we can get D. Once we get D, so we know R and we know the thickness W. So rearrange this equation in such a way that A is equal to this bracket multiplied by the factor of safety divided by SCL, which is the case here. So the factor of safety is 1.25 given. The mean and the reverse forces are the same. It's 2.5. Then KF was given in the problem, 3.46, and the yield strength of the material and the endurance strength are given. Then just simply this becomes 20.30 millimeters squared. If you equate this area here that you've got to this value, d squared over 4, so d squared over 4 is equal to 20.13. So this gives you the d value, and we know that d and r are equal, so d value is equal to r, and we know that r value is 4 times the thickness, or the thickness is 1/4 of the r. So if you divide this value by 4, so this gives you the w value. So this gives you the w value, or the thickness value. This is the end of problem number 6.